All right. Okay. Hello, various people in this room and also on the internet, if anyone is actually watching this on the internet. Okay. So, first thing that you have to do with these problems is that you have to do like the torque and stuff. So that's the thing where you use the distances to talk about rotation. So the pin is right here, so we're imagining if this thing is rotating around that pin, we're going to look at the distances from it, which are 14 here and 12 here, to these forces. So we have to set up our equation of the torque, which is going to be all of the forces that are acting on this object, all combined. So, and then we need the distances. So this one is 600 going clockwise, which we use as a negative sign. So it's going to be negative 600 times its perpendicular distance from the pin, which is 14. Then we are going to add our counterclockwise, or positive, from force times its distance perpendicular to the force itself. So we look at the distance that's perpendicular to the force. So that's times 12. And then plus our reaction force times the distance, which in this case our reaction is at the roller, and this is a distance of 9. So that will be times 9. And all this, if we're saying that the whole thing is not rotating, which we are saying none of this is rotating or moving, then this will be 0. So what we end up getting is 1200 equals the roller times 9, or the roller equals 133.33. So what this means is, because this is positive, it means that we're going to be going counterclockwise, or in this case, up 133.33. And so now that settles the rotation. We don't need any of the other stuff. The distances will not matter again. Once the rotation is done, none of the distance matters. So now we are looking at, is the entire object in motion, like up or down or side to side? So we're currently, this force needs to be balanced, this force needs to be balanced, and this force needs to be balanced. So currently we have 600 down plus 133.33 up, which is a total of 466.67 down. So we need a force to oppose that. So over here at the pin, it's going to be 466.67 going up. And you can just see, if you think about it, this is a force going up, this is a force going down, but the force going down is bigger, so we'll want to have the force at the pin be going up. But the other force at the pin, it will balance this horizontal force. So, and if you just imagine this whole box moving to one side, we're applying a force of 600, something else needs to be pushing 600 in the other direction. So this is going to be 600 in the opposite direction from the applied force. So those are all of the external forces. So now we have to look at the compression and tension in the actual beams. And so what we do is we look at a particular corner and we isolate that corner. And so this has a force of 466.67 on it, right? So this beam has to be able to take 466.67 force. Yes?
How do you decide which corner to start in?
So the corner you start in, you want the simplest one possible. So I'm starting here because this one is going only in the y direction and this one is going only in the x direction. So you don't have to do any trig or anything. And there are forces applied at this corner. So we know that this corner has to take 466.67 units of force. So it has to oppose with 466.67 units of force. And you see that if this was going up at all, we wouldn't know what to put because there would be multiple numbers for calculating it. If I was starting at this corner, I would know that I would have to have 133.33 down, but I wouldn't know how much would be on this beam and how much would be on this beam. But at this corner, the only way that you can get upwards force is on this beam. So that makes it simple. So this one will be 466.67. And now we know, because if this is pushing down, we know that this whole beam will have to balance itself out by having the same thing in the other direction, which gives us the 2 arrows on one beam. And now we can do the same thing with this beam, that we know there's 600 going this way, so the beam will have to resist with 600, and the beam will also have to push back on the other side, also at 600, so that everything's balanced. So, now we can move on to any other corner that we have information that we can do. So we can do this corner. So we know this beam is the only way we can have vertical force, and we need to balance out 600. So the vertical component of this force, if you can imagine it, this will have a horizontal component and a vertical component that will combine into the actual beam. And we need the vertical component to balance the 600 that is being applied at the corner. So when you do the trig, you will get 600 over sine of the value will be equal to our final force. And if you're wondering where this is coming from, it's that sine is equal to opposite over the hypotenuse. And in this case, we're solving for the hypotenuse, and we know what the opposite is because that's our vertical component that we're trying to get. So we know that this vertical component we want to get to be 600, and we're solving for the hypotenuse, and we get 960.46. And this is good because we also need to mark which way the arrow is going. So in this case, we know that the vertical component needs to go up to oppose the downwards arrow. So we mark the arrow in a way that it points upwards. And then at the other side, it will be going in this direction. So, but the one thing is, now that we have this 960.46, it's also creating an x component. So this side, this beam needs to be able to take the x component from here. And that x component is just going to be equal to the cosine of 38.6.66 times the value of the hypotenuse. Once again, that's the basic trig identity. And so that gives us a value of 749.99. So we solved that corner, and we solved these corners. And might think, because this is a harder problem, so you'll see that all the other corners from here on out have at least 3 beams. But we're going to go to this corner next because we've already solved one of those beams. So we know that this is pushing this way with 600 units of force. So the corner needs to push back with 600 units of force. But the only way it can do that is with this beam. So we know that the x component of this beam needs to point that way with 600 units of force. And so when we make the triangle, the cosine of this angle needs to be equal to 600. So we divide 600 by the cosine of 33.69 in order to get our hypotenuse, which will be the value of that beam. And that hypotenuse is 721.11. And we're opposing this force, so the arrow needs to point away, and this arrow balances over here. So that leaves, at this corner we have 1 beam left, and this is the vertical component. So the vertical component of the beam we just made is 721.11 times the sine of 33.69. And so that gives us a value of 533.33. But the other thing is we also have this force over here that's pushing up 133. And this one is also pushing up by 533.33. So, oh, actually, sorry, I skipped this step. So this one, let me find my notes. This one is pushing up by 400. This value actually calculates to 400. and then we add, so this one is pushing up by 400, and this one's pushing up by 133.33, which means the total force here is 533.33 units. So this beam needs to push down with 533.33 units. And so we have to balance out the beam by putting the arrow in the other direction. So now we've gotten a fair amount of this done. Oh, I forgot to sign this beam. So this one is pushing that way because it has to balance out the x component of this beam. So we've gotten a fair amount of this done, but this is where the problem starts to get annoying because we have to do some really annoying trig over here. So we know that up here we have 600 pounds of force, or pounds, whatever unit, are going to go in this direction. And we know that some of this is going to be taken out by the x component over here. And that x component we already calculated is roughly 750. So there are 750 pounds of force going this way along this arrow and 600 going this way, which means that there's a total force of 150 in this direction. So the x component of this beam needs to be equal to 150. So this angle, which is 33.69, if we take the cosine of that angle, and that would be equal to the value we want, which is 150 over the hypotenuse. So we can solve for the hypotenuse